So hello. Nice, such a full-packed room for maybe boring file format. But in the essence, file formats can be interesting, can make fun, and they're quite essential because you have data, you want to store it, you want to access it, and you want to access it again, maybe in a different fashion and maybe somewhere else. That's where Apache Parquet comes in. Shortly about me, I'm a data scientist. I work at a company dealing with supermarkets. I am an Apache Arrow and Parquet PMC, meaning Project Management Committee, fancy word for maintainer, and I'm a heavy Pandas user. In my talk, I'm going to give you a short insight of the history of Parquet, where it's coming from, why it was needed. I'm going to give you a more in-depth what the format is about, what makes the format special, efficient, and portable. And then there's also one slide with code, how you actually can use it, so you get access to it. Apache Parquet is a file format coming from the Hadoop space. It's a columnar storage format, basically meaning everything is each column after another is stored in the file. And it was invented 2012 by Cloudera and Twitter. At Twitter, they had a lot of log files. They were already serialized in a binary format, but they wanted to have them stored more efficiently so that they can also evaluate big, large queries on them. And in 2013, they made a first stable release of the format. And just some months later, it became an official Apache project and went into all of a lot other Hadoop-based projects, and now escaped a bit the Hadoop space and is now generally available. And since last fall, we have full support in Python and C++ for Parquet, both reading and writing. At the moment, it's a state-of-the-art format in the Hadoop ecosystem. If you have any kind of big, large chunk of data you want to process, normally tutorials will say you use Parquet. For example, in the Spark tutorial, I think if you look at the DataFrame tutorials, like 10 minutes in, they just say, okay, we started with JSON, but now to make full use of all power, use Parquet. Sadly, they just say use Parquet, they don't say why. And that's a bit why I'm going to give this talk, to give you a bit insight what's so fancy about this format. Parquet itself, it's a columnar format, meaning it makes vectorized operations, like if you have those fancy chips with SSE and AVX on it, really fast, but also because all the data in the column, which is of the same type, is stored nearby, you can also use like a more efficient compressing. There are two stages of compressing the data in Parquet. There is the encodings, which exploit that they know what data is in there. They're really effective. They're cheap, but they assume some things of the data, and they're just ordinary compression codecs, which run afterwards, making it a good combination and really fast compression, not so slow if you just use a normal compression algorithm like gzip only. And another important thing of the Apache Parquet format, it's not only made for that you can load and store data fast, it's also made that if you have a query you want to evaluate on a big data set, which is available in Parquet, that you can actually exploit some things in the data format, that you don't need to load the whole file, but that you only need to load the relevant bits which you need to execute your query. I'm going to a bit more detail on that later. And the last important thing, Parquet is language and framework independent. So it started off being used by Twitter for Hadoop, but they also used it in Cloudera's Impala. And it's now available in a lot more engines. So there are the two typical habitats of Parquet. It's where you have this big SQL query engines that can work on any file form, on any files in any file system, like Hive, Impala, Trill, or so on. They normally have, like Impala or Trill, they directly say use Parquet to get the best performance out of our engine. That's because they can exploit the format and don't need to load everything. And there are the frameworks like Spark and Hadoop MapReduce, that are the two common ones where you can use Parquet, where you actually get a tutorial set, okay, use this to get maximum performance. Nowadays, there's also support on Pandas to read Parquet files, and Dask has also support for using Parquet files input and output. And also there has been some benchmarks in showing that you can get a really good speed up in Dask, because already Dask It does not do all the magic you can do with Parquet, but it already does some of those, and therefore you get better partitioning or load less data. Now for the essence of Parquet. Parquet is in essence what you look at as a user. It's a file residing on some kind of file system, hybrid file system or S3 or your local file system. Normally Parquet files, you don't normally get one file. You have a big job that produces like 10 or hundreds or thousands of files. And a file here in Parquet dataset is normally just a file because a file system wants files. What Parquet has, from the global perspective, each engine looks normally at a Parquet file or dataset as a group of row groups. Row groups have all the same columns, and all the columns in a row group have the same length. And a row group is the highest level of parallelization you get. Normally, if you have 100 Parquet files and you start reading them in again from a computational framework, it will look and assign one partition or one job to each row group and not to each file. Often, one file has one row group, but in some other cases, a file can contain more than one. In each row group, we have those column chunks. Each chunk is of the same type. You have the same number of rows and same number of columns in each row group. And each column chunk is also made up of pages. Pages are like the smallest unit you have to load in a Parquet file. Pages are normally about 16 kilobytes big. That's the unit where you're going to do compression and encoding on. And if there's in a page a data point you want to load, you have to load the whole page. This is really relevant because if you're not loading the full file, but evaluating a query on it, Parquet provides on every level statistics. So then if you have a query which has a where clause in it and says filter on that condition, you can check on every level against the statistics if this condition is true, and then you only need to load this part of the file. And depending on the query, this can bring you down that you only need to load a single page of a column chunk. And then you only need to do the work on that, meaning that you get a lot cheaper access to this part of the file in comparison to if your whole file was one monolithic chunk and was compressed at once. And so you can use also every compression codec on there, even if this compression codec doesn't have some kind of like near random access support. There's compression and encodings. Encodings is the thing which is cheap, but also already bring down your data a good bit in size. They exploit that you know the data, and they also make assumptions about the data. So a typical thing, what is assumed is that there is some kind of repetition in your data, or that is some kind of redundant information which you can get away by doing intelligent encoding. Just for reference, I'm using the New York Taxi data set to give you an estimate about what are the size savings. That's kind of an average data set. It has some columns with repetitions in them, with a lot of repetition, and some columns with no repetition. The January data set was 1.6 gigabytes as CSV. The most basic encoding you can do in a file is just don't do any encoding, just save the data as is. This is very fast. It won't cost you any CPU. It is just memory copy. But if you use this, you probably will be limited by your I/O, meaning your network device is too slow or your hard disk is not as fast as your memory. So you already want to invest a bit more CPU to store the data a bit longer. The first and most important encoding is run length encoding and bit packing. Encodings are always simple. So the first one, bit packing, is quite easy. If you store data and your maximum value is maybe 4, then you only need 2 bits to encode 4, or in case it's 3, and then you only need 2 bits. And then if you have an int64, you can just press it down to an int2 and save that in your file. Already gives you a good number of savings. The next thing, if you're assuming there's some kind of repetition, you can use run length encoding. Run length encoding means just if you see some repetition, then write down it's a repetition, and this one will come like 200 times now. And what Parquet is doing, we're doing both of them at the same time. and we're always going to evaluate if it's worth doing, like writing down that we have a repetition, or the other case, there's a literal run, meaning we just write out the data as is. As an example, we look at this data here in chunks of 4. We see there's a maximum value of 1, meaning we only have 1 bit of information to encode for each value, meaning that we can go down to 1 bit. Also, in the first chunk, there is no repetition, or there is a bit of repetition, but they're not all the same. So it wouldn't be worth writing down there as a repetition. Because of that, we're just writing down it's a literal run, and it has the values 1, 0, 1, 0. And in the second half, there is repetition. All the values are the same. So we write down, we set the bit for repetition. We write down that are 4 values, and we put a 1 there. And this is done always on chunks of the data in Parquet. Actually, the base offset is if we have 8 repetitions of a value, we write down that's a repeated run. If it's less than 8 repetitions, it's not worth that. It's actually less amount of data to write down that there is the exact values. This is always done for things like repetition and definition levels. That's an important part of Parquet, which I'm skipping in this talk because it's kind of complex. But we have those two in the format to support nullability, that's definition levels, and the repetition levels so that you don't have just columns of primitive values, but a column can be a list of lists. We can encode that simply with the repetition levels. The second most important and most used also encoding is dictionary encoding. If you have worked with Pandas categoricals, it's kind of the same. The difference here is not done on a global file level or on a dataset level. It's done on a row group level. You take all the values you have, you assign each value a code, and then you store at the beginning of your row group the mapping of value to code, and further on you only use the codes. As an example, we have a list of colors, and to bring them down, we simply store the color names at the beginning and then have amount of data where we just have the codes for them. And these codes also only with the relevant bits we need. So we can, because there's obviously some repetition in these values, and because you don't need all bits, we're also doing this run length and bit packing encoding here on the orange section. And just doing this dictionary encoding, we already get down to 1/5 of the size of the initial data set. And the amazing thing is, dictionary encoding is normally so cheap that if you're reading from an SSD, you can read this file faster in comparison if it was just saved as it would be in memory. That already gives you a good benefit. But in the end, it assumes there's a repetition of data. And it works only on the data types if they're really repeated. If you have like floating point numbers which are nearly the same, dictionary encoding won't work that good. And for the cases where the encodings do not work good, or where we even want to improve a bit more, Parquet uses ordinary compression algorithms. But they're used after the encoding. So we already brought down our data set to 1/5 of the size. So we only have to push 1/5 of the data size to the compression algorithm, making the compression a bit cheaper than by doing it directly. There are 4 compression algorithms currently in the standard. If you want more, because of portability reasons, you have to extend the standard. The most dominant in there is Snappy, because Snappy already gives you a good size, but it's really fast. On the example data set, Snappy and gzip get you about in the same direction of the size. Gzip is a bit smaller, but in the end, Snappy is much faster. Also, there's a bit of portability. It's a portable format, but not all readers support all compression codecs. So Snappy is supported by everyone. Gzip is supported by everyone. I've said, oh, there are some licensing issues, so it's normally not supplied by default. And Broadly is the one which is new, which gives you, if you have gzip, normally it will always improve on your gzip. but it's not available on all engines. So I think at the moment it's only in Python and in Presto, and the pull request for all Hadoop best implementations is still open. So the basic usage is once you start using Parquet, just use Snappy. If that's a problem with performance, then think again, but at the beginning, don't care about and just use Snappy. So another important feature which makes Parquet a quite unique format is that it supports query pushdown, meaning that if you have a computational graph or an SQL query on it, depending on the engine, you already can push down the evaluation to the I/O layer. Because doing I/O is expensive, getting it faster gives you a bit better performance, but in the end, not doing I/O at all is the thing where you get the most performance out of it. Columnar format means Parquet, if you're doing something on Parquet files, you only need to load the columns you actually need. Meaning having a table, and we maybe have a query which only wants to evaluate all the yellow IDs where we have a price and dollar. We only need to load the yellow and the green column and can ignore everything else. That's mainly because we have a columnar format. The other thing is we want to skip rows or row groups which are not relevant for us. We have in the beginning I talked to you that we have those statistics at every level of the Parquet file. Most probably they are just minimum and maximum, but they already can tell you which group you don't need. If we assume these 3 rows are in different row groups, which is a kind of assumption only for the slides, we can see that in the middle column there is no dollar price. So through our query we also can skip over this data. And as it's with Parquet, we have in the metadata at the end already all locations of where a column or column chunk begins and ends. Thus, we already know where we have to skip. We don't have to read the data into memory and then skip in memory, but we already can skip on our I/O source, meaning that we will only load the non-shaded parts of the file here into memory, which is much faster than loading the whole file and then doing the computation in memory. Just as a comparison, Parquet files are quite small. This is the whole New York Texas data set for 2016. They're comparable to HDF5 and message pack. If you go here to the left, they're a bit smaller, mainly due to encodings. But I think depending on the layout of HDF5, I used the Pandas layout here. I think there are other layouts where it compresses a bit better. They're in the same region. How fast you can read them is also quite good. Using plain HDF5 is just really fast. I've done those benchmarks with a RAM disk, so there is no HDD overhead. And you can see the HDF5 is just immediately saved to disk, whereas if you have formats that have compression, it will take longer. The good thing about Parquet, I've showed you this picture of the file structure at the beginning. You can use the structure to read everything in extremely parallel, meaning that you can read each column chunk in parallel, or you can actually decode every page in parallel. Because you know how big each chunk will be in number of rows, you can already pre-allocate that and have several threads reading that in parallel, meaning that reading Parquet files scales really good with the number of CPUs. So with already 4 CPUs, you get to the baseline of HDF5. But in the end, we have a quite fast implementation here in Python, but where you can also see if you look at a comparison of storage size versus time to read, we have a good optimum down here with 4 cores, but also with single core, we're staying quite good. I obviously omitted here uncompressed HDF5. That's reading that is much faster, but the storage size is also a lot bigger. And for me, the most important issue Parquet should solve is the portability, that I have data in Pandas, can write it out, and read it maybe again with Impala or Drill to make SQL queries on that. But having this benefit that is also good in size and time and comparable to other formats is really nice. and was at the end it was only a byproduct being so fast. Mainly it was about portability. There has to be some code. So reading and writing Parquet is quite simple. At the moment it's available in Python via Apache Arrow, or if you want to pip install or conda install, the package is called PyArrow. What you're doing, this PyArrow package will call the C++ implementation, read it into an Apache Arrow table, and with the two pandas, or from pandas down here in the right path, you convert an Apache Arrow table to a Pandas data frame. A small, tiny bit of overhead, but that's neglectable in comparison to what amount of code we save. There are already now two implementations. There's the Arrow implementation, which is based on Parquet CPP, and there's a number-based one from Continuum called Fast Parquet. So I personally prefer the upper one because I wrote that, but there are two ones, and we have a bit of competition, meaning that we always take care to be fast. Because I just mentioned Apache Arrow, why do we use it? Apache Arrow is basically also standardization of data frames across different systems, so that you can pass data frames from system A to system B without having the need to convert something, or even depending on your language, if you're passing it from Python to maybe Lua or so, you don't have to make any copies. We used here Apache Arrow just to bring bindings to Parquet, meaning we have basically a lot of C++ code for the Parquet reader, which is really fast, and a tiny bit of like 100 or 200 lines of code, which glue all those methods we have brought in C++ to Pandas. I could make a whole talk about Arrow. We released 0.3 on Friday, so there's also included a new Parquet CPP release, which you can check out. It's already on Conda Forge. It's not on PyPy. That will be on maybe Monday or Wednesday. If you have questions to that, you can ask me later, but this talk is about Parquet, so I'm skipping over this. Also, it's an open source project, so instead of the typical we're hiring, there is a get involved slide. I will post those slides on my Twitter account and in the Slack channel. But get involved. We have not implemented all features of Parquet in Python yet. And at the end, you can do a lot of stuff more. At the moment, you can only load data frames and store them again. Dask already have some optimizations that you only load the row groups you need. But things like query pushdown are not yet implemented in Python. But that's the thing, if you want to evaluate big queries on it in a query engine, that's what you really need. But it might be also useful for someone in Python. Yeah, and that's it. Questions?
How do you explain the size, the difference in size for the HDF5?
The question was here, the difference in size between Parquet and HDF5. I'm not sure why this is. Could be due to the layout of Pandas, because there are different layouts. You can store HDF5 files. I would have expected that HDF5 and message pack would perform exactly the same. But you can store data frame differently in different HDF5 files, and I use the standard Pandas implementation.
What about null values?
Parquet can store null values on every level. So if you have a list of lists, you can have a null list, or you can have null entries in lists. Because data is loaded back in Pandas. Pandas has only those float nulls at the moment. Integer columns with nulls will be float column in Pandas. Apache Arrow doesn't have that, so once Pandas supports real null values, we also have them then from Parquet and Pandas. Yeah.
How are they compared to org files?
Org files and Parquet files are quite the same. So I think the main difference is where your ecosystem's a bit. So if you're in Hadoop, if you have a Hortonworks sponsored product, they will normally prefer org files, and other projects will prefer Parquet files. But they're kind of the same format, not the same format. They have different things implemented, but they're in the same scope, and they're doing the same things and have the same features from a user perspective.
work well on Hadoop file system, or is it the block size is too big for it to be useful?
Parquet files are normally on Hadoop file system, so that's where they started. And that's where if you can normally say the size of a row group here.
Yeah.
And if your Hadoop file system, the perfect row group size is a Hadoop file system block size.
Okay.
But you can have them somewhere else. So I'm using a lot of Parquet, and we don't have a Hadoop file system at our company. So it works very well.
How is write performance for different write behaviors, say appending or random inserts?
So the question was write performance for different behaviors. There's actually only one way. Parquet files are write once. So you can't append to them. And because compression is done on these page levels here. And at the end of the file is the metadata. So you want to written the metadata, the file is done. Write performance is quite good because you're doing all this compression and encoding, and because you can even do that partly in parallel. We don't have it fully in parallel now. It goes quite well. It's less than read performance, but in my benchmarks it was about 1.5 times the read performance.
Also built on Arrow is the feather format from West McKinney and Hadley Wickham. Can you say anything about how this relates?
Yeah, the relation to the feather format is that feather is just taking data as it is in memory. It takes the same bindings and same file structures as Parquet CPP is using to write down all files, but feather is unstable, and Parquet has has a specification which is a bit discussed between different teams and have several readers, and it's made for long-term storage, and it's also made for these query push-down things. You can't do a really good query push-down in Feather, and Feather is mainly to have a really fast exchange if you're on the same system but want to switch between R and Python or so.
Did you say you can't currently read a single column in the Python writings, or you can?
You can.
You can.
Yeah. Yeah.
So if the Python Parquet libraries support data structures with nested and repeated fields like JSON?
The question was, the Python libraries support nested fields. At the moment, only lists of lists. We have an open pull request, which is making like structures of lists or dictionary of things, but it will take hopefully a month, but then we have it. There's always the representation in Python, because if you have a list of lists, this is normally a NumPy array of Python objects, so it's quite inefficient, but you can encode it. The Apache arrow structures can hold these things efficiently, but you can't access that at the moment really good. So that's hopefully a thing that comes with Pandas 2, but Pandas 2 is quite on a long horizon.